Thanks for a kind introduction and this great opportunity to share my work with you today. And yeah, so today I would like to introduce how we can utilize the artificial intelligence to do like this kind of facial phenotyping and further help us to facilitate the diagnosis of rare disorder. Okay. Okay, yeah. So this is my today's outline. So first of all, I would like to introduce how this kind of technology works with like a facial analysis. And this technology we also refer to as next generation phenotyping. So this is more like trying to echo the next generation sequencing. However, it doesn't really limit it to only to the facial analysis. We can also apply to like hand X-ray image analysis or brain MRI or fetus ultrasound. So, but today I'm only focusing on the facial analysis in today's presentation. And the second part of my presentation, I will introduce the Gestalt measure database. So the reason why we want to set up this database, one reason is because there's no public available database that can be shared with the medical um, researchers, so people cannot see the photos directly, and also the computer science doesn't have the resource to train their models. And the second reason to build up this database is because, as we know that the majority of the data coming from the Caucasian, so we would like to set up this database to cover the diverse population. And in the end, we know that this kind of technology is not perfect, just like general AI is not perfect. There's a lot of limitation. So we would like to introduce the limitations to the current technology. So just like this figure on the very right-hand side, I used the ChatGPT to generate this figure. And as you see that this figure doesn't look very good, very good. So that's why we know that there's still a lot of limitation and we need to know how to use it correctly. Yeah, so at the beginning, you might wonder, so why we can diagnose the faces by looking at the faces, why we can diagnose the disorder by looking at the faces. So here I take the three patients with the Collinear de Lange syndrome as example. So you might already observe some facial pattern presenting on their faces, which is their eyebrow. So they all have the synovius. So it's like eyebrow will be connected, and also sometimes their eyebrow will be very thick. So this is just one of the key features in this disorder. So that's why we know that we can try to uh, look at the faces to recognize the facial patterns to further diagnose the patient. So what we can do is that we can simply just train some deep convolutional neural network by thousands of patients' images to try to learn the facial representation of the disease and further quantify the similarity score to the patient on the very left-hand side to the disorder we train on the network, which is the syndromes we train in the network on the right-hand side. And so, for example, we can try to quantify the similarity score between this patient to the four syndromes on the right-hand side, which is the Noonan, Cohen-Cyrus, HPMS, and Kabuki syndrome. And here, for example, we can see that the Cohen-Cyrus one yield the highest similarity score. Then we can further check the mutations in ARID1B and to find out the disease-causing mutation and to further diagnose this patient. And this technology we often refer to as the next generation phenotyping. And the next generation phenotyping is very popular over the last few years. So it starts from like at the very beginning in 2014, the Ferry et al. They published a paper in eLife, and they trained a model on more than 1,000 photos with 8 different syndromes. So they are also the first one to propose the idea of the clinical face phenotype space, which I will also introduce later. And after 5 years, in 2019, um, the company called FDNA, they published a work called Deep Gestalt in Nature Medicine. So they trained a model on over 21,000 images with around 216 syndromes. And they further also launched this approach in the well-known platform called Face2Gene. So it is used by thousands of clinicians every day, and they only focus on classifying the different disorders. So which is on like the figure show on the left-hand side. So you input the image and try to classify the disorder which train in the network. And after 3 years, we work together with FDNA. So we trying to push the limitation of this deep Gestalt approach to from like 200 disorder up to 1,000 disorders. So we further published together um, Gestalt measure approach in Nature Genetics. So the main difference between these two methods is because we can analyze the similarity between the patient or between the images. We're not no longer just limited to do the prediction to the disorder we train in the network. And I will also further introduce this method later in the following presentation. Yeah, so first of all, you might wonder why we are focusing on the rare disorder. We don't have a huge data set. Why we can train a model to learn the facial phenotype of the disorder. So we use the technique called transfer learning. So the transfer learning, the concept is that we start training the model on more like the very general task. Then later we fine tune the model on the very specific task. So for example, here we take the healthy individual, like mainly from celebrities, from the Cassia web phase. So there are around like 500,000 healthy individuals in this database. So the first training is that we train the deep convolutional neural network to learn how to classify different persons. So for example, we try to classify between Matt Damon and Mark Wahlberg. So I have to admit, I think they are very similar. So I finally realized they are different persons after I got my PhD. And yeah, so the first training is like trying to classify different persons. So that's why we know how the human face look like. And the second step is like we just replace the last layer, the classification layer from different person to different disorder. So so for example, here we just keep training the model on 20,000 images, patients' images. And so for example, here on Coffin Cyrus, Progeria syndrome, and also Cornelia de Lange syndromes, then we can know how the facial phenotype look like. So with this kind of technology, then we don't require like 500,000 patients' images. We only need around like 10,000 or 20,000 images, then we can try to learn how different disorder look like. And this technology is called Deep Gestalt, and which is published by FDNA back to 2019. Yeah, so this is the screenshot of this paper. Yeah, however, although we know that this kind of technology is very powerful and can classify around like 200, 300 disorder and with a very high accuracy, but the problem is still because the distribution of the rare disorder is very biased. So for example, here I just trying to um, use the pathogenic submission from ClinVar to do the simulation of how the distribution of the rare disorder look like. So for example, I just downloaded data from ClinVar and I count how many pathogenic submission every gene. So for example, on the x-axis is how many submission per gene and y-axis is how many genes. So, and then we can see that on the right-hand side, just for example, there are around like 10 genes with more than 2,000 pathogenic submission. Maybe we can just try to assume that one submission is one patient. So here we can see that on the very left-hand side, so there are around 2,600 genes, which is 53% of the genes with less than 10 submission. So it means that the majority of the data, the majority of the genes or disorder has very, very few patients. So this is like the general situation in the rare disorder. So and then we can see that around only 300 or up to 400 disease genes with less than 10% of disease genes with more than 100 submission. However, it somehow influence how we train a model because so we are using the deep learning. We need a huge amount of data to learn the facial phenotype. So it means that if we don't have enough photos for this disorder, we are not able to really train a model for this disorder. So then as we can see that the majority of the disorder has very, very um, few patients. We don't have really enough the photo to train a model for them. So that's why we need to come up a new method. So we after the first publication from Deep Gestalt, we further work together with FDNA. So we come up another approach called Gestalt Matcher. But the base model is the same, still like a deep convolutional neural network trying um, to train a model to classify the different disorder. But the next step, oh, sorry. Oh, sorry. So the next step is different. So what we do is that we take the last layer before the classification layer, which is the blue model here. So we take this layer as the feature layer. So we assume that this layer, because this layer is contributing the last layer, which is the classification. So we assume that this layer can contain some key facial features. So for example, maybe it's the size of the nose, the size of the eyes, or the distance between the eyes, and also maybe the thickness of the eyebrow. So this kind of the last layer, which is around like 320 dimensional feature vector. So we assume that this feature vector is the key um, feature to contribute the final classification. Yeah, so as we know that the upper part is what we know is from Deep Gestalt, which is launched in Phase 2 Gene. And what's the difference is that we take the last layer, this blue node, as a feature layer. So each node can be represented as a one 320 dimensional feature vector. Then we just use this high dimensional feature vector to span another space called clinical phase phenotype space at the bottom. So here we can see that so each photo is a point located in this space. Then we can further do some downstream clustering analysis for the photos. For example, we can see that the patients with similar, um, the patient with the same disorder will cluster together in the phenotype space. Then the main difference here between the deep Gestalt and Gestalt matcher is that, as we can see that here there's a red box. There are only two patients with this disorder. So we can also match the patients uh, with the disorder with only one patient. So for example, as long as they are similar, they will close in the space. So we no longer restrict to maybe we need to have at least 6 patients or at least 10 patients to train the disorder in the classifier on the top. So that's why we can further push the limitation of around 200 or 300 disorder up to around 1,000 or further to 2,000 disorder, supporting disorder. So then this is the main difference between these two methods. So the upper part is what FDNA published back to 2019. We refer to as the big deep Gestalt, and the lower part is the Gestalt metric. Yeah, so the main concept in the Gestalt measure is that in the phenotype space or in the clinical facial phenotype space, if the patient have the same disorder or have the similar facial phenotype, they will locate close to in the space. So for example, on the left-hand side, we use the t-SNE to try to project them into the two-dimensional figure. So each dot here is a photo. So here we can see that the patients with Coven Cyrus, they are close together, or Noonan syndrome, they are also close together. So we can further just use some distance metric. So for example, we use cosine distance to try to quantify the similarity between the patients. So if you have, so for example, if the patient have a very small cosine distance, it means that they are very close in the space. It represents that they have a very high facial similarity. Yeah, so the next point, maybe you might wonder, so in the end, how do we do the prediction or how we evaluate the performance of the of Gestalt measure? So what we can do is that, so first of all, the left-hand side is the patient we want to test, and then on the right-hand side is um, is the phenotype space. Then we can further just trying to um, populate the phenotype space by thousands of disorder or by the patients with thousands of disorders. Then what we can do is that we further just put this patient into the space. Then we're just trying to find out the nearest neighbors in the space. And so, for example, on the left-hand side, we can see that there are around like the 5 patients. I just try to get it from this space. And we can just check the syndromes of these patients, as we can see that the top rank, the first rank of the patient also have the Covan virus. Then we call this top one match because this patient also have the Covan virus. And later we have another example, which is the patients with Noonan syndromes. Then we just put this patient also into this space. Then we also try to check what is the disorder of what is the disorder in the space, which is also close to this patient. And we find out another patient with Noonan syndromes is in the fifth position. And so we call this as a top 5 match. Then it also applies to top 10 or top 30 match. And after our publication in 2020, we further try to improve the base model and also the architecture of the deep convolutional neural network. The reason is because in the Gestalt method, the first publication of Gestalt method, we used the same architecture and the pre-trained model back to 2014 because we want to have the fair comparison with the deep Gestalt method. So it is relatively, although it is classical network, but it is relatively old, outdated. So what we do last year is that we try to use the ResNet and also the larger pre-trained model to improve the diagnosis, to improve the accuracy. So for example, here is the comparison between the Gestalt measure approach from the 2020 and 2023, which is the one we published last year. So as we can see that the top one accuracy is increased from 15% up to 52%. And the top 10 accuracy is also increased significantly from 45% up to almost 80%. As we can see that, so if we can try out a new method or we can try out different latest technology, then we can further improve the accuracy significantly. So this is also one key point we want to convey in our the second part of the presentation, which is the Gestalt measure database. So the reason why we think the reason why this field progress relatively slowly compared to the computer science research field is because the people don't have the fair database or the public available database they can benchmark. So only a very limited group in this work can work on this field. So because you need to collect around like 10,000 image by your own. So I think this is very difficult. A lot of group cannot have the resource to do this to collect this such huge collection. So yeah, so I will also try to introduce this part later in the second part of my presentation. Yeah, so as we know that we can try to we can try to have a suggested list uh, from the syndromes in close in the phenotype space. So what we do is that we launch a platform called Gestalt Measure Database, and we also you can also try to predict the disorder, the patient of the disorder in the website, and also we also provide like a iOS app and also the Android app, then people and the doctor can also just take the photo and get a diagnosis. So we are also trying to do some research on this app in the like a pediatric department in Germany. So we want to test whether this kind of application can really help them to do some diagnosis. Yeah, so the next point is that we can also try to integrate this kind of analysis into the exome analysis pipeline. So for example, we can just take the photo of this patient and we can quantify the Gestalt score to each gene or each disorder we have in the database. Then further, the most naive way is that we can just simply add one more column with like Gestalt score into the variant prioritization platform, which is on the right-hand side. So you can further check the facial similarity for each variant or for each gene in your platform. So yeah, so we already provide this kind of implementation. So we can just simply provide a Docker image. So the bioinformatician in your lab or in everyone's lab can further just integrate this software into their pipeline easily. Yeah, so the next part is that we can not only just provide this similarity score in your pipeline, we can also try to contribute to the ACNG variant classification. So especially this is very important to help to facilitate the diagnosis of the variant of unknown significance. So for example, and we can just take the photo and try to quantify the phenotype match by the facial image analysis. Then we can try to quantify whether we can reach the PP4 supporting or PP4 moderate or even to the PP4 strong criteria. Then we can further push the variant of unknown significance to to further to likely pathogenic or further to pathogenic classification. So here is just one example how we do it. So we follow this paper from Taftigian back to 2019. So he proposed this ACNG variant classification based on the Bayesian framework. So what we do is that, so this is just one example of the collinear de Lange syndrome. So what we do is that they defined a threshold based on the likelihood ratio. So for example, for the very strong, they define like, so your likelihood ratio need to achieve at least 350, and for strong is around like 18, moderate is 4.3, and supporting is around like 2.7 or 1.7. Yeah, so if your score can reach this threshold, then you can call it is very strong or moderate. So for example, the blue line is the likelihood ratio of the collinear de Lange syndrome with Gestalt measure. So as we can see here, so if your score can reach higher than 0.4, then we can say that, okay, so this patient achieved the PP4 very strong. And for strong is around like 0.33. So if your Gestalt score for collinear de Lange syndrome or to NIPBL is higher than 0.33, then we will call it, okay, you have PP4 strong. And for the moderate is that if you have around 0.28, higher than 0.28, then we call, okay, you have the PP4 moderate for this disorder. And further down to maybe around 0.21 for the PP4 supporting criteria. Yeah, so for this way, we can just further to provide this additional ACNG classification, then we can further help to push the VUS up to likely pathogenic. Yeah, another thing we also try to do is in our clinic, so we try to integrate the facial analysis together with the other type of the data, such as the HPO term, the human phenotype ontology analysis, and we try to integrate the facial analysis, HPO analysis together with the exome data analysis. So this is what we published back to 2019. We call it PDA approach, the prioritization of exome data by image analysis. So in this work, we try to do is that we try to take the photo of the patient, and also we encode the clinical report into HPO terms, and we try to integrate with the exome data. So in the end, we can just try to in the end, we just generate a final variant report based on these three information. Yeah, so this is just some illustration of the work, how our work look like. So the input as you can see that input is like we have the symptom, which is the HPO terms of the patient, and we have the facial photos, and in the end we also have like exome data, and so for the benchmark we need to know the disease-causing mutation. So what we do first is that we just use different HPO analysis approach. So for example, like the phenomizer or the BOCA, and to quantify the phenotype, the feature match score. The second part is that we use the deep Gestalt approach in the Face2Gene platform to quantify the Gestalt score. So one of the reasons we use the deep Gestalt in this paper is because it is published back to 2019. So at that time, the Gestalt measure is not there yet. So that's why we just use the deep Gestalt in Face2Gene platform to quantify the facial Gestalt scores. And in the end, we just, because some of the data, we don't have the whole exome, we only have the disease-causing mutation. So we have to simulate the exome of the patient. So we simply just take the healthy individual from 1,000 genome dataset, and we just put this disease-causing mutation into this into this exome, then to simulate the exome of this patient. So we further just annotate the CAR-score and do the allele frequency filtering. Then we just get the CAR-score for each gene, which is on the bottom part here. So in the end, so each gene will have 5 different score, which is the 3 score from the HPO analysis, and 1 score Gestalt score from the facial photo, CAR-score, which is from the exome data. And here in the end, we just, for each patient, we will have around like 100 or 200 genes with this 5 score. Then we just, in the end, we train the support vector machine on around 697 patients to train the model. And in the end, we can provide a PDR score for each gene for each patient. So, and this is just one result for this patient with the ARID1B, with the disease-causing mutation in ARID1B. So here we can see that, so the ARID1B of the PDR score, oh sorry, the y-axis is the PDR score, x-axis is the chromosome position of each gene. And here we can see that ARID1B, which is on the very top, yield the highest PDR score, which is the correct answer of this patient. So this is just one way we can use the PDR score, or we can integrate the facial analysis into your variant prioritization pipeline. Of course, it doesn't really limit it to utilizing either the Gestalt measure, face or deep Gestalt, or phenomizer or CAR-score. So this is just a concept that how we can integrate different score into the variant prioritization pipeline. And also, this is also one concept that the facial analysis can contribute to the final diagnosis. Yeah, so further, we just trying to apply Gestalt measure and the PDR approach in our latest German National Rare Disorder Project. So this is the 3-year project back to 2019. So what we do is that, so we collaborate with 16 German university hospital, and we sequence around, I think we sequence around like 4,000 patients, but in the end we only achieve we sequence around 1,500 patients, and in the end, we diagnose around 32% of the patient, which I think is a very general accuracy or general performance. And so this is the publication we just published last month. And what we do, one of the key findings related to today's presentation is that we try to validate whether the facial analysis can help the diagnosis of the exome data. So for example, here on the figure on the right-hand side here, there are 2 lines related to today's presentation. Is the blue line. The blue line is when we include the facial analysis. And the orange line is that if we don't include the facial analysis. Here we can see that it's the blue line, including the facial analysis, is clearly outperformed if we don't include the facial analysis. And of course, we don't just try to do the validation on the method we mentioned above, like use the CAR-score or use the phenomizer, and together with the facial analysis. We also try to benchmark different kind of variant prioritization methods, just like lyrical, exomizer, X-ray, and Emily. So we simply just add the facial analysis addition to list 4 different methods. So as we can see that the blue line here is also outperform the orange line. So again, the blue line is including the facial analysis, and the orange line is without the facial analysis. Yeah, so with this study, we know that so including the additional facial analysis can increase the diagnosis the accuracy. Yeah, so Kushida or this kind of facial analysis can not only just contribute the diagnosis, we can also try to delineate the facial phenotype of the given disorder or the given gene. And so what we can do is that we already try to analyze around 21 novel disease genes and the facial phenotype of novel disease genes, and 18 of them were already published in a peer-reviewed journal or in the Med archive. Yeah, so although at the very beginning I tried to introduce and what the AI or what the next generation phenotyping approach can achieve. However, we still have a lot of limitation. So for example, one of the key limitation is that um, whether we want to know whether the AI will be confounded by the ancestry. So as we know that the majority of the training data coming from Caucasian patients. So usually a lot of people from like African country or from Asian country, people just question about whether this kind of technology can really help for like an Asian patient or for African patient. So here we just take this very extreme example here, trying to answer this question, whether the AI can be influenced by the ancestry. So, for example, we try to train the deep convolutional neural network on very two bias distribution. So, for example, we try to train the Cornelia de Lange patients only from the European. So all the European with the Cornelia de Lange patient, the Cornelia de Lange syndrome, sorry. And another cohort is the African patient. However, the African patients are all with the Williams-Borden syndromes. So then here we have a question is like, if we have another patient, which is the African child with the Cornelia de Lange syndrome, what will be the output of this classification or will be this neural network? What is will the neural network will tell us this is Cornelia de Lange syndrome or the Williams-Borden syndromes. So I believe maybe the network will tell us, okay, this patient is the Williams-Borden syndrome. So the reason is because maybe the network is already learning the color of the skin. It's not learning the facial phenotype. So then we know that okay, so this is the African patient. Then the network think okay, then this patient must have the Williams-Borden syndrome. So therefore, this is one problem. Like if we have a very biased data set, this might be the problem. And this is also one very famous situation back to I think back to 2019. There is a Dr. Rumaka from Congo. He just reported one situation from phase 2 gene at the very beginning, because Rumaka have a lot of like Down syndrome patients, which is also the African patient. So he's one of the very first African doctor to upload a lot of African patients. So he upload a lot of African patients with Down syndrome. And afterwards, he realized that every time he upload, he tried to predict or try to diagnose a patient with this kind of approach, African patient with this kind of approach. Every time, it always return Down syndrome. So because the system already learned that, okay, African patient, Down syndrome. So that's why we really need to have a diverse data set. It means that diverse syndrome and also diverse population. Yeah, so our the main goals of our next project is like we want to provide a diverse data set for the computer scientists that they can try to develop the new method, a new NGP method for diagnose the patient with the facial images. And also we want to provide this diverse resource for the clinicians so they can directly see how the patient look like. And for example, they can directly see how the African patient look like or Asian patient look like. They can have a more diverse reference data set. Yeah, so this is the first overview how this Gestalt metric database look like. So we mainly collect the facial photos of the patient. So we collect around almost around like 11,000 images of around like 900 disorders. So this is just an overview of how the user can see it or how the researcher can see it in our platform. So they can see the photos directly, and they can also search for their favorite genes, maybe an NIPBL or maybe also you can also search for like Kabuki syndrome. You want if you want to know how Kabuki patient look like. Yeah, so this is just some statistic of this database. So we have already around like more than 11,000 images, and it comes from around 8,000 different patients in the database. And these 8,000 patients also cover around 900 disorders. So, and here we, at the very beginning, and we start to try to curate from the publication. So our medical student just read around like 2,000 publication and try to annotate the data into the database. And afterwards, we also collaborate with some patient support group and also some clinic directly. So some clinicians will just contribute the data directly into a database. If they don't want to publish as a case report, then they publish in our database. And also some patient support group, they are the parents were also very eager to contribute the data because they also want to help to have a better technology, then it can help for their children's in the future, they can diagnose faster. Yeah, so the database is not really public available, so we need like an invitation link to access the database because we don't want the people can search in the Google, then they can register directly without any access control. So if you would like to access this database or register in our database, you can scan the QR code on the right-hand side, and I will also show this QR code on the upper right corner in the following slide. Yeah, so as we pointed out at the very beginning, one of the goal of this database is trying to have the diverse population, cover diverse population. However, even though we try to work over the last few years, so the distribution is still very biased. So for example, here we can see that there are around 67% coming from the European ancestry and 19% from Asian and 7% from African countries. And the Asian here is include like a Middle East, East Asian, or South Asian, which is already very diverse population. However, we only have 19% of the data coming from Asian countries. So that's why we further trying to improve this kind of situation. We further also collaborate with some local clinic or some clinicians in like South America country, like in Brazil or in African countries. So we have like we have a four collaboration in the African country or in also in the Asian countries. So we would like to just trying to keep working on this topic and improve the diversity of the population in this data set. And one very important message in this figure is that this figure is, we already distorted this figure based on the birth rate. So we can see that the African country have a very high birth rate, which is larger. It also, we try to increase the size of the continent by the birth rate. And here is the India. And as we can see that the European ancestry country will be relatively small because the birth rate is relatively low. So that's why we know that. So it is very urgent or is very crucial if we can improve the support to like African country or like the South Asian countries here, because for this country in this region have a relatively high birth rate. Yeah, so as we pointed out at the beginning, is that we collaborate with around more than 100 clinicians from more than 100 different institutions. And in this data set, we already have around like 2,300 previous unpublished images. It means that so these images are not published in any case report yet, and it might come from the parents directly or coming from the some clinicians directly, because maybe the clinician doesn't want to spend the time to publish the case report anymore because maybe this kind of disorder have a relatively low scientific value. So for example, maybe it could be Down syndromes, or it could be like Cornelia de Lange syndrome, because people already know the faces very well, so they don't need to publish the photo anymore. So, however, so every one photos is very variable for the deep learning technology because we really need the photos to work with um, to improve the accuracy. Yeah, so this is just another visualization how what this platform can provide. So first of all, we can provide like an overview, a gallery view in the database, and so not only we store not only the facial photo, although the majority of the data is the facial photos, we also store like the profile and also like so the hand images. Sometimes we also have the hand X-ray or brain MRI images. And we also have like we also if the data is coming from the publication, of course we need to store the source of the where the data come from. Maybe it's from this publication, and we also store like some patient information, like when is the photo is taken. So, for example, we take the photo from 8 months old, 9 years until now 25 years old. So with this longitudinal data, then we can try to analyze how the facial features progress over the time. And in the end, we also store some molecular information like what is the disease-causing mutation, and also what is the HGBS code and or the of this mutation. Then we can further do the downstream analysis. Of course, we also store some phenotype information like HPL terms of this disorder, whether this patient have the seizures, developmental delay, for example. Yeah, in the end, the user can also, or the clinicians can also do some analysis in our platform. So they don't need to really download the data and also uh, set up all the software to do the analysis. Yeah, so one of the key goal is to analyze the ancestry in this data set. So I would like to show you why the diverse data set is very important. So for example, here we take around 3,100 images with the European from the European patients in GNDB to train as the base data set. And we built the first model is that we have additional 1,500 European images. So we use this around like 4,600 images together to train the first model, and this model is very special is because this model only seen the European. And then we want to have the comparison to the model, not only just seen the European, which is on the right-hand side. So we train another model is that we replace these 1,500 European patients with non-European images. So both data set have the same number of the images, which is for the fair comparisons. However, the distribution of the ancestry is different. So this model not only just see the European, but also 1,500 non-European patient. Then we want to know how these two model perform on the test set, which is the diverse population. So for example, here we trying to benchmark this method on the different ancestry, which is on the right-hand side. Each bar is different ancestry. So for example, this bar is the European, and this bar is the East Asian patients. So the blue bar here is the model only see the European. And the orange bar here or the yellow bar here is the model not only see the European, but also see the non-European patients. So here then we just want to compare how the performance change between these two models. So first of all, we can see that most of the population um, uh, will be benefit from this diverse model, which is the yellow bar here. So all the yellow bar is higher than the blue bar. However, only just one exception, which is only one exception, which is the European patients here. We can see that so the European patients achieve higher performance in the European model. So this is also very trivial because the problem is that the European model already fine-tuned too much on the European patients, so that's why they recognize very well of the European patients. So that's why the performance will drop down a little bit if we if we include the diverse population into the model training. So one of the very important here is like especially for the Southeast Asian. So here we can see that there is a huge performance increase from 20% up to 70%. Yeah, so as we can then we know that so the diverse population in the training set is very important. Otherwise, if we only use the very biased data set, only the European patient will benefit from the data set. Yeah, so and we already have this work in the published the preprint in the medRxiv. So if you are interested in our study, you can scan the QR code on the left-hand side. You can find our publication in the medRxiv. So, and as we pointed out at the very beginning, so one of the key contribution of this data set is that this will be the first data set that comply with the FAIR principle. It means that the people in the research community can use this data set for their own research, maybe for the NGP development. So this is just one example from our collaborator from the United States, from the Children's Hospital of Philadelphia. So they try to integrate the facial image analysis and together with demographic information like the cell sex or the age or ethnicity, and also with the clinical note, which is maybe developmental delay or sleep disturbance and so on. They try to integrate, they try to use the vision language transformer to integrate these three different information in the end to do the prediction, which is maybe Cornelia de Lange syndrome or Noonan syndromes. So GNDB is one of the data set they use for training the models. So and also do the benchmarking. So with this kind of data set, it's very important is because then we can try to benchmark different method with the same data set. Otherwise, every research group can say that, okay, so we cannot share the data, you cannot benchmark on our data set because this is our the data in our hospital, so we don't want to have some issue with the patient or the concern. And then everyone only develop their method based on their local private data set, then it is not really helpful for the general research community because people cannot benchmark. We are not able to really say like, okay, this method really improved the accuracy because we all benchmark on different data set. So that's why this is just one example how GNDB can contribute to this research field. Yeah, another thing how this kind of technology can help is that so one of our collaborator from NIH, they try to do some survey whether the synthesized phase can also help for the medical education. So the synthesized phase is that so nowadays we can try to synthesize the fake facial images. So not only just the general the fake images, but also we can also generate like a fake patients. So for example, we can generate like a Cornelia de Lange faces or Noonan faces. So and in this publication, they just prove that the synthesized face can only help the clinician to learn the facial phenotype of the disease. Yeah, so as we know that, okay, so nowadays we want to know what will be the next in this technology. So this is one of the key publication I just want to introduce in the previous slide. So this is the one publication published by our collaborator in the NIH. So they try to do the proof of concept, try to synthesize the face of the Williams-Borden syndrome and 22q deletion, so they can try to synthesize the patient's face and also with the different age. So, and this is also a very key publication over the last 2 years because, and in this way, we can try to have a larger data set for the training because we can synthesize the fake faces, and we can also share this data without any consent issue. Yeah, so in the end, what will be the next? So we just try to envision like maybe this kind of facial analysis technology can also try to apply in different kind of data set, data type. Maybe it's the fetus image or fetal ultrasound, brain MRI image, or maybe we can try to integrate this technology into the newborn screening and so on. Yeah, so this is also one of my favorite slide, and what will is this kind of technology will be the future. So the reason why I like this slide because I can watch this movie in my office for 2 hours. So and because I told my boss I need to make this slide, so I need to watch these movies. Yeah, so this is one of my favorite movie. It's like there's like a med part, so they can just examine the humans and do some surgery, whatever, get a diagnosis. So we just wonder, is this really the futures? So I think this is a very intensive discussion, like whether the AI will replace the medical doctor or whatever in every field. But I think this is in my opinion, I sometimes feel is a little bit exaggerate. So because I think now we expect that AI is just trying to help the medical doctor to do their work, just like we use like Grammarly or whatever ChatGPT to help with our like daily work to maybe write an email and so on. So yeah, and because one of the reasons why I think the AI is still limited is because we know that AI is not perfect. Just like we know that the current technology sometimes is just like black box. So for example, if the Gestalt measure or deep Gestalt, whatever, it tell you this is Collinear de Lange syndrome. So, but it still cannot tell you why they think it is Collinear de Lange syndrome. So, so for example, they cannot tell you like, okay, because there is a synovitis, because there are some features, so that's why the models tell you think this is Collinear-de-Lange syndrome. Maybe the model just judged by the background. Maybe the Collinear-de-Lange syndrome patient always have the white background. So this is the reason. So we don't know whether we can rely, we can trust the AI because we don't know how they predict. So for example, this is one of the work we trying to do or everyone try to do is the explainable AI. So here we can see that we can try to visualize which part of the faces contribute to the prediction. So these two are the Collinear-de-Lange patient. Although we can see that we try to highlight the mid face here, which is the eyebrow or the middle of the eyebrow. Yeah, of course, we know that this might be the key feature because we have some medical knowledge, like, okay, it might be the synovitis. However, we still don't know whether this is really a synovitis caused this to contribute the diagnosis because we don't know whether it is because of synovitis or because the sick of the eyebrow or because this patient doesn't have any eyebrow, just for example. So we still need to have more and more explanation of the prediction. Just like if you ask a question in ChatGPT, you want to know why he make this uh, suggestion. You were asking, okay, so what is the reason? Maybe the ChatGPT will just output more and more reason to convince you this is why I think this is the diagnosis. Yeah, so in the end, we will try to find out, also trying to find out whether the machine think is the same as the humans. But the first step is that we need to know how the human look at the patient. So that's why we just use the eye trackers. So we do a study together with our collaborator in the NIH. So we use this eye tracker and we ask the clinician to see the patient's images in the screen. Then we can further try to measure uh, how much time they spend in each part of the face and also what is the order they scan through the faces, just like maybe they start from the eyes and the nose and the head, the forehead, for example. Yeah, in the end, we're just trying to measure whether whether there's the overlap between the clinician and the machine. So left-hand side is the heat map from the clinician, and right-hand side is the heat map from the machine. So then we're just trying to calculate the overlap between these two heat maps to see whether the machine also observe or examine the same location as the humans. So, however, we also see that it really differs from uh, syndrome to syndromes. Yeah, this is one of our preliminary work published early this year in PLOS Genetics. So Yeah, so we are still planning to do a larger study, which is based on the different ancestry of the clinicians. So maybe Asian clinicians looks differently from the European clinicians or from the American clinicians. And yeah, so this is one of the ongoing study we are still trying to work on. Yeah, in the end, just some take-home message. So although we know that NGP has some potential to improve the diagnosis, but we know that AI is not perfect, so we need to know how to use it correctly. And yeah, and still lots of limitation, like we need to have a the data set with a diverse population, and also we need to improve the interpreting how we can interpret the model prediction. Then we can trust this technology. Yeah, in the end, I would like to thank everyone and involved in this study and also the patient and their family. And thank you. I'm happy to answer all the questions.